Students, in this part of the D and F block elements, we are going to discuss F block elements in this video lesson. The F block elements consist of two series of inner transition elements, that is lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinium. These elements are also called rare earth elements. Although lanthanum does not have any 4f electrons, but this is included in the discussion of lanthanoids due to its close resemblance with lanthanoids. Similarly, actinium is included in the discussion of actinoids. Now we are going to discuss lanthanoids first. All the lanthanoids have electronic configuration with 6s2 common, but with variable occupancy of 4f and 5d subshells. The electronic configurations of the elements with fully filled f orbitals and half filled f orbitals are relatively more stable. For example, in europium, the 4f orbitals are exactly half filled, and in the element ytterbium, the 4f orbitals are fully filled. Now we will discuss some properties of lanthanoids. First we will discuss about atomic and ionic sizes. The atomic radii and ionic radii of tripositive lanthanoid ions show a steady and gradual decrease with the increase in atomic number is called lanthanide contraction. Now we will discuss the cause of lanthanide contraction. As the atomic number increases in lanthanoid series, for every proton in the nucleus, the extra electron goes to fill 4f orbitals. The 4f electrons constitute inner shells and they show poor screening effect. Therefore, there is a gradual increase in the effective nuclear charge experienced by the outer electrons. Consequently, the attraction of the nucleus for the electrons in the outermost shell increases as the atomic number of lanthanoids increases and the electron cloud shrinks. And this results in gradual decrease in size of lanthanoids with increase in atomic number. Now, the consequences of lanthanoid contraction. The first is similarity of second and third transition series. The atomic radii of second row of transition elements are almost similar to those of the third row of transition elements. For example, zirconium and hafnium, they have almost similar sizes, and this is due to the lanthanoid contraction. In this case, the usual increase in size on moving down the group from second to third transition elements is cancelled by the decrease in size due to lanthanoid contraction, due to which they have nearly similar atomic sizes. All the lanthanoids have quite similar properties, and due to this reason they are difficult to be separated. Also, the basic strength of hydroxides decreases from lanthanum hydroxide to lutetium hydroxide. This is also due to the lanthanoid contraction, due to which the size of their tripositive ion decreases and the covalent character increases. The main oxidation state shown by lanthanoids is +3. Few lanthanoids show the oxidation states of +2 and +4, yet they have the tendency to attain the oxidation state of +3 because the +3 oxidation state is most stable state for all lanthanoids. That is why the lanthanoids like cerium and terbium in their +4 oxidation states have a tendency to come to the more stable oxidation state of +3 by gaining electrons and act as good oxidizing agents. And the lanthanoids like europium, samarium in their +2 oxidation states have a tendency to come to the +3 oxidation state, which is more stable, by losing electron and act as good reducing agent in their +2 oxidation state. Now we are going to discuss some general characteristics of lanthanoids. Lanthanoids are silvery white metals having low tensile strengths, and their hardness increases with increasing atomic number, and samarium is very hard. Now, regarding the melting and boiling points of lanthanoids, They have fairly high melting points. However, no definite trend is observed in melting and boiling points from lanthanum to lutetium, but their melting points range between 1000 to 1200 Kelvin. But the melting point of samarium is 1623 Kelvin, and they have typical metallic structure. Many of the lanthanoid ions are colored in solid state as well as in solutions, and this is due to FF transitions, just like DD transitions in transition elements. It is because they have partially filled f orbitals, and the ions in which the 4f orbitals either empty or fully filled, those ions do not show any color. The lanthanoid ions are paramagnetic in nature due to the presence of unpaired electrons, except those in which 4f orbital are either empty or fully filled. Lanthanoids have fairly low ionization enthalpies, due to which they have high electropositive character, and their first and second ionization enthalpy values are quite comparable to those of alkaline earth metals, particularly calcium. The first ionization enthalpies of lanthanoids are around 600 kilojoule per mole, and the second about 1200 kilojoule per mole. In their chemical behavior, in general, the earlier members of the series are quite reactive, similar to calcium, but with the increase in atomic number, they behave more like aluminium. Many lanthanoids react with carbon to form salt like carbides, and with hydrogen to give salt like hydrides. Lanthanoids react with oxygen and sulfur to form oxides based on formula Ln2O3, and sulfides based on formula Ln2S3, where Ln is the general symbol for lanthanoids. They form halides with halogen, and they liberate hydrogen with acids. They form nitrides with nitrogen, and they form hydroxides and liberate hydrogen when reacts with water. Now the uses of lanthanoids. The best single use of the lanthanoids is for the production of alloy steels for plates and pipes. And the mish metal, an alloy which contains rare earth elements nearly 95% and iron 5% and traces of sulfur, carbon, calcium and aluminum. This mish metal is used in magnesium based alloy to produce bullets, shell and lighter flint. Mixed oxides of lanthanides are used as catalysts in petroleum cracking, and some of the lanthanoid oxides are used as phosphors in television screen and similar flossing surfaces. The series of elements involving the filling of 5f orbitals is called actinoid series, and the actinoids include the 14 elements from thorium to lawrencium. The chemistry of actinoids is more complicated due to the existence of greater range of oxidation states for these metals. Moreover, all these metals are radioactive with short half lives, due to which their study is more difficult. If we look at the electronic configuration of actinoids, then atoms of these elements have electronic configurations with 7s2 configurations and variable occupancy of the 5f and 6d subshells. Now we will discuss the variation in their ionic sizes. There is a gradual decrease in the size of their atoms or their trivalent cations across the series, and this is called actinoid contraction, just like lanthanoid contraction. If we compare the actinide contraction with lanthanoid contraction, then actinoid contraction is greater from element to element than lanthanoid contraction. This is due to the poor screening effect shown by f electrons in actinoids. Actinoids exhibit greater range of oxidation states in comparison to lanthanoids. This is due to the fact that 5f, 6d and 7s subshells are of comparable energies. The common oxidation state of actinoids is +3. However, they also exhibit the oxidation state of +4, +5, +6 and +7, and the +2 oxidation state in actinoids is quite rare. Now we are going to discuss the general characteristics and their comparison with lanthanoids. The actinoids are all silvery white metals and they get tarnished when exposed to the attack of alkalis. All the known actinoid metals are highly electropositive and they resemble lanthanoid series in this respect. The actinoids are paramagnetic due to the presence of unpaired electrons. However, the magnetic properties of actinoids are more complex than those of lanthanoids. All the actinoids are radioactive in nature, whereas all the lanthanoids except promethium are non-radioactive. The ionization enthalpies of early actinoids are lower than those of early lanthanoids. Now we will discuss the general characteristics and comparison. Now we will discuss some applications of D and F block elements. Iron and steel are the most important construction materials which belong to the D block. D block elements or their compounds like titanium oxide, these are used for the pigment industry. The compounds of manganese like MnO2 and nickel cadmium and zinc, these are used in the battery industry to prepare the cells like nickel cadmium cell, zinc mercury cell, and in dry cell MnO2 is used. The UK coins, which is called silver, is the alloy of copper and nickel, and many of the metal transition metals and their compounds are used as a catalyst in the chemical industries. For example, vanadium pentaoxide is used in the manufacture of sulfuric acid, whereas iron catalysts are used in the Haber's process for the production of ammonia from nitrogen and hydrogen mixtures. Actinoids, being radioactive in nature, they are used in different fields. For example, thorium, uranium, and plutonium, these are used as a fuel for atomic reactors, and thorium is also used in the treatment of cancer.